Where he sees your head, my lovely, we sleep her with my hate. Or for me think that we give his crulf, he cries said. Your honours, ere I shall, Gromas. No, I haven't just had a stroke. Don't call 911. I've just written a basic artificial intelligence to generate Shakespearean text. Now we get to finally address the question, which is better, writing Shakespearean sonnets, a billion monkey hours, or a poorly trained AI? Let's get started. Alright, first, before we begin with our imports, a couple of administrative notes. The first of which is that this is an official TensorFlow tutorial. I have not written this code myself, and in fact it is quite well written, as it is the first tutorial I haven't had to make any corrections or adjustments to. So I will leave a link in the description for those that want to go into this in more detail on their own time. So feel free to check that out when you have a moment available. Second point is that my new course, Deep Q-Learning from Paper to Code, is on sale for about the next week or so, the next 6 days. The MLK Day sale is still going on today, and after that I'll be running my own promotion. So check the link in the description and or pinned comment if you want to learn how to turn deep reinforcement learning research papers into Pythonic PyTorch code. Let's get started with our imports. The first thing we want to import is OS. That will handle some operation OS level type stuff. We want TensorFlow as TF, of course, and we want NumPy as NP. Now, notably, we are not importing the TensorFlow dataset imports because this is not using an official TensorFlow dataset. Rather, it is using the data due to, I believe, Andre Carpathy gets the credit for this, but it is basically a text representation of a Shakespearean sonnet. Which one, I don't know. It doesn't state in the tutorial, and I am not well read enough to be able to identify it based on the first several characters. I suppose if I printed out enough of it to the terminal, I could figure it out based on who's in it, but I don't know, and it's not really all that important. But what is important is that we have to download it using the built-in TensorFlow Keras utils. And of course, they have their own function to get a file, and it's just a simple text file called Shakespeare.text, and that lives at https storage googleapis.com Shakespeare.text. Okay, and so let's get an idea for what we're working with here. So let's open it up in read binary mode with an encoding of UTF-8. And let's go ahead and print out the length of the text. So we'll say length of text blank characters dot format len text, and let's go ahead and print the first 250 characters to get an idea of what we are working with. All right, let's head to the terminal and test this out. Say python tf-text-gen.py. Object has no attribute decode, so I have messed something up. Most likely a parenthesis somewhere, text equals open path to file.read. That's right, I forgot the read method. Insert read dot decode. There we go. Let's try that. Perfect. So now we see that we do indeed have some text, and it has 1,115,394 characters, so a fairly lengthy work, several 100,000 words at least. And you see it begins with first citizen. This is important because we're going to refer back to this text a few different times in the tutorial. So just keep in mind that the first word is first. Very, very simple. And hey, if you know what play or sonnet this is, leave a comment down below because you're more well-cultured, more well-read than I am. I would be interested to know. But let's proceed with the tutorial. Let's head back to our file, and the first thing we want to do is comment these out because we don't want to print that to the terminal every single time we run the code. But the first thing we have to handle is vectorizing our text. Now, if you have seen my other 2 tutorials on natural language processing and TensorFlow, you know that we have to go from a text-based representation to an integer representation, or in some cases, yeah, totally integer representation, not floating point, in order to pass this data into the deep neural network. So let's go ahead and start with that. So we say our vocabulary is going to be sorted a set of the text. So we're just going to sort it and make a set of unique stuff. So we'll say print, or unique words rather, blank unique characters format len of vocab. So now important thing to keep in mind is that we are starting with merely characters. We are not starting with any conception of a word. So the model is going to go from knowing nothing about language at all to understanding the concept of words, as well as line breaks and a little bit about grammar. You kind of saw from the introduction that it's not so great, probably better than the monkeys typing away, but it is, starting from complete scratch into something that kind of approximates language processing. So we have sorted our vocabulary. Now we have to go from the character space to the integer representation. So we'll say char to IDX, where char is just, character. That's going to be a dictionary of unique characters and their integer IDX, their integer encoding for IDX unique and enumerate vocab. Closing bracket. And we need the IDX to char, which is the inverse operation, numpy array of vocab. Then we have something called text as int, and that's a numpy array of a list comprehension of char to IDX of char for char in text. So we're just going to take all of the characters in the text, look up their IDX representation, and stick it into a vector numpy array in this case. So now let's go ahead and print this stuff out to see what we're dealing with, to see what our vocabulary looks like. And we'll make something pretty looking. We'll say for char blank and zip char to IDX range 20. We're only going to look at the first 20 elements. We don't need to print out the whole dictionary. Print 4s colon 3d dot format representation of the character char to IDX char, and then at the end we'll print a new line. Actually, let's do this too. So we'll say print blank characters mapped to int. You know how many characters will be mapped to int. Dot format representation of text, just the first 13. Text as int 13. Tab that over and write this and run it. Do unexpected end of file while parsing. Okay. So what that means is I have forgotten a parenthesis, which is here. Perfect. Now we can write quit. Now let's give it a shot. Okay, so you can see we have 65 unique characters. So we have a dictionary of 65 characters, and new line maps to 0, space maps to 1. So basically it's the sort has placed all of the characters, the non-alphanumeric characters at the beginning, and we even have some numbers in there. Curiously, the number 3 maps to 9, but whatever. And then you see we have the capital letters, and the lowercase letters will follow later. And so our first sentence is first citizen, first 13 characters rather, and that maps to this following vector here. So we have gone from this string to this vector representation. So that is all well and good, but that is just the first step in the process. So the next step is handling what we call the prediction problem. So the real goal here is to feed the model some string of text, and then it outputs the most likely characters it thinks will follow based on what it reads in the Shakespearean work. And so we want to chunk up our data into sequences of length 100, and then go ahead and use that to create a data set. And then from there, we can create batches of data, in other words, chunks of sentences or chunks of whatever sequence length characters we want. Let's go ahead and go back to our Vim editor and start there. And so the first thing is we want to go ahead and comment all this out because we don't want to print everything every single time, and then handle the problem of the sequence length. So we'll say sequence length equals 100 characters, something manageable. You don't want something too small, something too large. So number of examples per epoch equals line of text divided by sequence length plus 1. Where does a plus 1 come from? It comes from the fact that we're going to be feeding it a character and trying to predict the rest of the characters in the sequence. So you have the plus 1 there. Next we have a char data set, TF data set. Of course, it's TensorFlow. It has to deal with its own data sets. It doesn't handle text files too well. So we're going to go data set from tensor slices text as int. Let's go ahead and print out what we have here for I in char dataset dot take the first 5 elements. And so this is just a sequence of individual characters, so we should get the first 5 characters out. Print idx to char i.numpy. Let's go ahead and go to the terminal and run this. Right quit and run it once more. And you see we get the word first. As one would expect, that is the, if we scroll up, that is the first 5 characters, first and then citizen. Okay, so that seems to work. So now let's handle batching the data. So let's go back to our Vim editor, get rid of this print statement by inserting a couple of comments, and worry about dealing with a batch. So sequence says equals char dataset dot batch sequence length plus 1 drop remainder equals true. So we just get rid of the characters at the end. For item, can I scroll down at all? Does it let me do that? No, it does not. One of the downsides of Vim as an editor. So for item in sequence is dot take 5, the first 5 sequences of 100 characters. Print representation blank dot join idx to char item dot numpy, and a whole bunch of parentheses. And let's go ahead and go back to the terminal and see how this runs. So let's run it. And you see, I really should put a new line in there at the beginning, but you can see first citizen, before we proceed any further, hear me speak, blah, blah, blah. So we get a bunch of character sequences, including the new line characters. So that is pretty helpful. One thing to note is that these new lines are what give the deep neural network a sense of where line breaks occur. So it knows that after some sequence of characters, it should expect a line break because that formulates, the kind of metered speaking that you find in Shakespeare. So that's well and good. Let's go ahead and handle the next problem of splitting our data into chunks of target and input text. Remember, we have to start with one character and predict the next set of characters. So let's handle that. But of course, to begin, we want to comment that out. And in fact, do we need this? No, let's leave it in there. It's not going to hurt anything. So we'll say we're going to define a function called split input target, and that takes a chunk of data as input. And it says input text equals chunk, everything up to -1, target text equals chunk 1 onward. Return input text target text. So we're going to get an input sequence as well as a target. So we want to double check this by saying data set equals sequences dot map. I'm going to map this function onto our sequences, split input target. Let's add in a new line for clarity and say, you know what, let's do this. There we go. So we'll say we're going to print the first examples of the input and target values. Say for input example, target example in dataset.take, just the first thing. Print input data representation blank.join idx2 char input example.numpy whole bunch of parentheses, print target data representation blank.join idx2 char target example.numpy. All right, let's head to the terminal and try this. Okay, so you see our input data is this first citizen before we proceed any further, and it ends with U, and then the target data is erst citizen. So given this input, what is the target? So we have basically shifted the data one character to the right for our target with respect to our input, and that's a task. Given one character, predict the next likely sequence of characters. So to make that more clear, let's go ahead and kind of step through that one character at a time. So let's come down here, and of course the first thing we want to do is get rid of these print statements, and then say for I input IDX target IDX and enumerate input example first 5 target example, I forgot a zip statement 5, how many, that's the enumerate, that gets a colon, I forgot my zip here, in enumerate zip, add an extra parenthesis, and then we want to add a print statement. We will say print step 4D dot format I print blank input some string dot format input IDX representation of IDX2 char input IDX print expected output yes dot format target IDX comma representation IDX2 char target IDX. All right, now let's head to the terminal and run this, and we should get something that makes perfect sense. Name input example is not defined. Okay, so input example, oh, of course I got rid of this. All right. All right, so here you can see the output. So step 0, the input is an integer 18 that maps to the character F, and the expected output is I. So it knows that it should expect the next character, which is the next character in the sequence. Now keep in mind, this isn't trained with an RNN yet. This is just stepping through the data to kind of show you that given one character, what should it expect next. So that's all well and good. The next thing we have to handle is creating training batches and then training our model, building and training the model. So let's head back to the text editor and handle that. So let's go ahead and comment all this out and handle the conception of a batch. So we'll say let's handle the batch size. Next, we'll say batch size equals 64, and buffer size, just how many characters we want to load, 10,000. Data set equals dataset.shuffle, buffer size, dot batch, batch size, drop remainder equals true. Then we want to say vocab size equals len of vocab. We're going to start building our model next. So embedding dimension 256, RNN units 1024. So we will use a function to go ahead and build our model. We'll say def build model, vocab size, embedding dim, RNN units, batch size. Model tf keras sequential, tf keras layers, an embedding layer. Of course, we have to go with an embedding layer at the beginning, because if you recall from the first video, we have to go from this integer representation to a reduced dimensional representation, a word embedding that allows the model to find relationships between words. Because this integer basis, all of these vectors are orthogonal to one another. There's no overlap of characters. However, in the word embedding, the higher dimensional space or reduced dimensional space allows you to have some overlap of relationship between characters. So those vectors are non-orthogonal. They are to some extent collinear. So just a bit of math speak for you, but that is what is going on there. Vocab size, embedding dim, batch input shape equals batch size by none, so it can take something arbitrary, and that. Next layer, tf keras layers, a gated recurrent unit, a type of RNN, that is RNN units, return sequences equals true, stateful equals true, recurrent initializer, yeah, I think I spelled that right, glow rot uniform. Is that right? Yep. Okay, so now we have another layer. Let's tab that over. Say tf keras.layers.dense, and it'll output something of vocab size. So now let's end that and return our model. So now that we have a model, the next thing we want to do is build and compile that model. So we'll say model equals build model, vocab size equals len of vocab. Yeah, this is one kind of thing I don't like about the tutorial. Embedding dim, there's a little bit of that little bit right there, but whatever. Embedding dim, and we need RNN units equals RNN units. Batch size equals batch size. So that will make our model, and let's go ahead and see what type of predictions that model outputs without training. So we'll say for input example batch, target example batch, and data set dot take one. Now keep in mind this is going to be quite rough because there is no, there's no training yet, so it's going to be garbage, but let's just see what we get. So we say example batch predictions equals model input example batch, print example, let's print the shape, example batch predictions dot shape, and that should be batch size, sequence length, and vocab size. And you know what, while we're at it, let's just print out a model summary so you can see what's going on and see what is what. So let's head to the terminal, try this again, see how many typos I made. Batch input shape, that's probably a batch input shape on line 77 right here. Batch size, what have I done? Something stupid, no doubt. Oh, it's probably here. Batch inputs shape. There we go. Try it again. Okay, so you can see that it has outputs of something batch size by 100 characters by vocab size. Makes sense. Here is the model, 4 million or so parameters. They're all trainable, and you can see that the majority of those are in the gated recurrent unit. So let's go back to the text editor and start thinking about training the model. So we come here, let's go ahead and get rid of this print statement. We don't need it. We can get rid of the model summary as well and think about training our model. The first thing we need to train the model is a loss function. So we'll pass in labels and logits and return tf-keras losses sparse categorical cross entropy labels logits from logits equals true. And then since we are good Python programmers, we will format this a little bit better like that, and we can go ahead and start training our model. So we will say model.compile and optimizer equals Adam, loss equals loss, and say checkpoint directory equals dot slash training checkpoints, checkpoint prefix equals os path join checkpoint dir checkpoint underscore epoch. So epoch is a variable. It's going to get passed in by TensorFlow or Keras in this case, and so it'll know whatever epoch we're on. It'll save a checkpoint with that name. Checkpoint callback. You have to define callbacks. tf.keras.callbacks.model checkpoint file path equals checkpoint prefix save waits only equals true. And so we'll train for, in this case, I don't know, something like for reference, I trained it for 100 epochs to generate the text you saw at the beginning of the tutorial, but it doesn't really matter all that much. So we'll say 25 epochs because it's not the most sophisticated model in the world. So we'll say history equals model.fit, dataset epochs equals epochs, callbacks equals checkpoint callback. All right, let's head to the terminal and run this. It says expected string bytes, not a tuple. Okay, so as path join that, I probably made some kind of silly mistake. It says checkpoint dir, that is a string. Checkpoint underscore epoch is fine. That's interesting. What was that error? That is on line 91. Oh, I understand. So I have a comma there at the end, so it's an implied tuple. Okay, let's try this again. Scratching my head trying to figure that one out. All right, so now it is training. So I'm going to go ahead and let this run, and I'll be back when it is finished. Okay, so it has finished training, and you can see that the loss went down by a factor of 3 or 4, about 3 or so, from 2.7 all the way down to 0.77. So it did pretty well in terms of training. Now, this is 25 epochs. We don't have to rerun the training because we did the model checkpointing. So the next and final order of business is to write the function to generate the predictive text, the output of the model. So that way we can kind of get some sort of idea of what sort of Shakespearean prose this artificial intelligence can generate. Let's go ahead and head to our file. So the first thing we have to think about is how are we going to handle loading our model, and that will require that we don't do the build model up here, so we can just get rid of that and we certainly don't want to compile or train the model again. We want to load it from a checkpoint. So what we'll do is say model equals build model, vocab size, embedding dim, RNN units, and batch size equals what? Batch size equals 1. That's right, because when we pass in a set of input text, we don't want to get out, a huge batch of output text. We just want a single sequence of output text. And then we say model.load weights, tf.train, latest checkpoint, dir. So this will scan the directory and get our latest checkpoint. And then we want to build the model by saying tf tensor shape 1 by none, so batch size of 1 and an arbitrary length of characters. So then we'll say model.summary, and we can scroll down a little bit for readability. So that'll print out the new model to the terminal. So the next thing we have to handle is the prediction problem of generating text. So let's say define generate text model and start string. So we need to pass in the model we want to use to generate the text, as well as a starting string, a prompt for the AI, if you will. Generate equals 1000. That's the number of characters we want to generate. Input eval equals char to idx s for s in start string. We have to go to the character representation of, the integer representation of our characters, and then we have to expand that along the batch dimension. We need an empty list to keep track of our generated text, and a temperature. So the temperature kind of handles the surprising factor of the text. So it'll take the text and scale up by some number. In this case, a temperature 1 means just whatever the model outputs. So a smaller number means more reasonable, more predictable text, and a larger number gives you some kind of crazy, wacky type of stuff. So let us reset states on our model and say for I, let's scroll down, for I in range num generates predictions equals model input eval, predictions equals tf squeeze along the batch dimension 0, predictions equals predictions divided by temperature, and predicted ID, which is the prediction of the ID of the word returned by the model. TF random categorical predictions num samples equals 1 minus 1 0 dot num pi. Then we say input eval equals tf dot expand dims predicted ID 0. Text generated dot append idx2 char predicted ID. So if you're not familiar with this, the random categorical is a probability distribution when you have a set of discrete categories, and it will predict them. Oh, I forgot a 1 here that will break. So it will generate predictions according to the distribution defined by this variable predictions. So then we want to return start string, and that may be familiar to you if you watch some of my other reinforcement learning tutorials. The actor-critic methods in particular use the categorical distribution. Plus empty string dot join text generated. So then you want to say print generate text model start string equals Romeo colon. Give it a space as well. All right, now moment of truth. Let's see how well our model does. Write that, go to the terminal, and try it again. So you see it loads the model pretty well, and we have our text. That is quite quick. So King Richard III says, I will practice on his son. You are beheads for me, you, Henry. Brutus replies, and welcome, General, and music the while. Tyrrell, I'm wondering if these aren't the collected works of Shakespeare, actually, now that I'm reading this, looking at all of the names. That's kind of Brutus and King Richard. That sounds like it's from a couple of different plays, Caesar and whatever King Richard appears in. I don't know. Again, I'm an uncultured swine. You let me know. But you can see that what's really fascinating here is that this model started out with no information about the English language whatsoever. It knew nothing at all about English. We didn't tell it that there are words. We didn't tell it that there are sentences. We didn't tell it that you should add in breaks or periods or any other type of punctuation. It knows nothing at all. And within, 2.5 minutes of training, it generates a model that can string together characters and words in a way that almost kind of makes sense. Now, Bernardine says, I am a Roman and by tenot and me. Now, that is mostly gibberish, but I am a Roman certainly makes sense. But Warwick, I have poison that you have heard, that is kind of something. To add mine own port and process of that hung and point, okay, that's kind of silly. Is pointing that my soul, I love him well. So it strings together words in a way that almost makes sense. Now, returning back to the question of which is better, 1 billion monkey hours of typing or this AI, my money is solidly on the AI. These aren't put together randomly. These are put together probabilistically, and they kind of sort of make sense. And you can see how more sophisticated models like the OpenAI text generator could be somewhat more sophisticated using transformer networks, and how they can be better at actually creating text that even makes even more sense. Although what's interesting is that it's not a significant quote-unquote quantum leap. I hate that phrase, but it's not a quantum leap over what we've done here in just a few minutes on our own GPU in our own rooms. That is quite cool, and that is something that never ceases to amaze me. So I hope you found this tutorial enjoyable. If you have, make sure to hit the subscribe and the bell icon, because I know only 14% of you get my notifications. Once again, a reminder, my new course is on sale. I can't stop shilling it. It's just in my blood. Go ahead and check that out in the link below it, either description or pinned comment. And look forward to seeing you all in the next video.